Hyvää päivää. Hyvää huomenta. I'm very honored to be the first chairman of the first session of the keynote speakers of the second International Tampere Conference on Statistics. It gives me tremendous pleasure to introduce the first keynote speaker, Professor T.W. Anderson from Stanford University, who was my teacher 20 to 25 years ago as a graduate student, and has remained a close friend and collaborator over the intervening years. His book, now in a second edition on multivariate analysis, is the book, at least for me, in multivariate analysis. He's going to talk today on multivariate linear relations. Professor T.W. Anderson.
Well, you see, it's worth your while to be kind to your graduate students. You never know when they're going to get back to you. It's an honor and a privilege for me to lead off the keynote speakers, to lead off the conference. My talk is on multivariate linear relations, which seems appropriate for this conference. It is in keeping with the tradition that's been established by the first conference. Now, first, let me discuss linear structural relations as one model which has been treated considerably. In this case, we have an observed vector x, which is decomposed into two unobservable vectors. The first one is considered as the systematic part, and the second one as the error. The first one is supposed to satisfy some linear equations, so it varies in a lower dimensional space. The second vector, the error, is random. We take the mean to be 0 and some covariance matrix sigma, and sigma is supposed to have a structure, and there's several alternative kinds of structures that are considered there. A related model is the factor analysis model, where the observed vector x is considered to be a linear combination of the components of an unobserved vector f, the factor scores, and an error again. In the factor analysis model, the covariance matrix of the error is assumed to be diagonal, so the components are uncorrelated. Now, you see that these models are essentially the same if you consider the unobserved vector y, in the first case, to be written as lambda f. And writing this as lambda f indicates that that vector varies in some lower dimensional space. Usually the number of components in f is much smaller than the number of components in x. Up in the linear structural relations, we also had the systematic part in a lower dimensional subspace. These are equivalent in the case that the matrix beta in the first representation times the matrix lambda of factor loadings, if that product is 0. And of course, we want the dimensions to correspond. Now, the factor scores, the latent variable may be random or maybe non-stochastic or a mixture. We shall first consider that the factor scores are random, and we standardized by having the mean vector 0. The covariance matrix is labeled phi, and an important assumption is the factors and the errors are uncorrelated. Recently, I got back a paper submitted to the annals with a comment of the referee that I didn't use the conventional notation, and the paper should be rewritten to use the conventional notation. In factor analysis, the notation is very much a tradition, more so even in the Tampere conference. Now, from these assumptions that we've talked about, we can describe the distribution of the observed vector x. I call its covariance matrix sigma. Its mean is mu because f and u both have mean 0. And when we make use of the lack of correlation between the factor score and the error vector, you see that this covariance matrix involves the quadratic form and the factor loadings, and we have the matrix of covariances, well, really variances, because this matrix is diagonal. So we're considering that the observable covariance matrix is a matrix, positive semi-definite matrix of lower rank, plus a diagonal matrix. Now, the factor scores represent a coordinate system in the lower dimensional space, and might be not necessarily an orthogonal coordinate system, and there's an indeterminacy there of what coordinate system to use. So for many purposes, we want to eliminate that ambiguity. One way of eliminating it is to ask that a submatrix of lambda is the identity. In that case, if that's a requirement, then you have eliminated any possibility of multiplying lambda on the right by an arbitrary non-singular matrix, and at the same time making that linear transformation or the inverse on factor score. If the indeterminacy is eliminated, then we say that the parameters are identified. Unfortunately, the word identification is greatly overused. I think the econometricians got a head start and used identified to have the meaning that I'm using in this lecture. But as you statisticians know, there are several other uses of that term. Now, the other representation has an indeterminacy too, because those equations can be multiplied on the left by an arbitrary non-singular matrix A. So to eliminate that indeterminacy, we may ask that a submatrix is the identity. Now, we saw earlier that the linear structural relations and the factor analysis model are the same, or equivalent, if the product of those two matrices is 0. And with these identification conditions, that means that the sum of the remaining matrices, submatrices, are 0. The point of this is that if the linear structural relations have an error covariance matrix that's diagonal, then an estimation or testing procedure for factor analysis automatically gives one for the linear structural relations. Now, I want to talk today about a generalization of these models. So let me define the class of models that I'm going to consider. So we have the observed vector x, which is linear combination of fixed but usually unknown vector mu, and then a linear combination of subvectors, which I label z sub g, which are unobservable. And the purpose of having these subvectors is to indicate the uncorrelatedness of those subvectors. So these subvectors have mean zero. They have arbitrary covariance matrices, but the different ones are uncorrelated. So just as in the factor analysis model, the errors and the factors are uncorrelated, here these subvectors are uncorrelated. Now the loading matrices I've written as being possibly functions of some parameter vector lambda in order to give the generality to this class of models. Now let me show that this is really a generalization of the factor analysis model. At the top we have the factor analysis model, and I've rewritten it again with the identification on the matrix of factor loadings, and I've written out the components of U in detail. But this can be rewritten with a vector taken from the identity times the first coordinate of U, another vector, column vector, from the identity times the second component of U, and so on. So this is that's written in a very long-handed way in terms of my general model as indicated here. The vector lambda, of which those matrices, capital lambdas, are functions, that it consists of the free elements of the vector, of the matrix lambda star. Now we could put other requirements on these components of lambda star and write that in the form of functions of the parameters that are not assigned. Now what are the objectives in this study? Well, first of all, when the latent variables are normally distributed, we can obtain the maximum likelihood estimates of the covariances of those unobserved quantities and of the vector little lambda, which determines the loading matrices. And again, given normality, we can ask what's the asymptotic distribution of those maximum likelihood estimates. We expect that to be normal. But thirdly, we can ask about the distribution when we do not have normality. And as we will see, we do not need to require that these are normal, but nevertheless we get the same asymptotic distribution. It's sometimes called asymptotic robustness of the, in this case, maximum likelihood estimates. There are computer programs for these kind of models, and they're based on numerical evaluation of, numerical determination of maxima and evaluation or approximation of the covariance, asymptotic covariance matrix that goes with it, but all of this under the assumption of normality. And the result of this study is that these asymptotic standard errors are valid whether the factors or other latent variables are normal or are not normal. One of the results of this study is an outgrowth of some work that I did with Herman Rubin for the Third Berkeley Symposium, and that was picked up more recently by myself and a collaborator. Michael Brown and Alexander Shapiro have gone further with this, and in particular have considered the model which I've just presented. But my approach is different from theirs, and the results are stronger. So let me now start with assuming that our observations, capital N of them, are from a normal distribution with a covariance matrix that's determined as indicated earlier, then we will use for inference the sample covariance matrix. And under normality, that sample covariance matrix has the Wishart distribution. I've written the density here, which I assume is well known to all in the audience. Point is that the density depends on the covariance matrix and the sample covariance matrix in this fashion. Now, how does the covariance matrix depend on the parameter? Well, first of all, what are the parameters that we have? We have the covariances of the unobserved z's, which we define as capital Phi of g. If we take those terms and form them into a vector, use the lowercase letter phi, and then we have the factor loadings depending on a vector of parameters lambda. Now remember, the x is a linear combination of the z's, so the covariance matrix, which I've calculated here, is x minus mu times its transpose. And the form of this results because the different z's are uncorrelated. So in forming this product, the expected values of different z's are zero. That is, the products of different z's are zero. So we're ending up with this covariance matrix. So our problem is to take we're going to use the Wishart likelihood function, consider the covariance matrix as this function of unknown parameters, and then obtain the maximum likelihood estimates of those parameters. Now, I've written down the model in quite general terms, and you might ask, well, if you actually knew the population covariance matrix, could you determine what those parameters are in the linear structure? We need to make sure that we can go from the sigma to the theta, that is the parameters of the latent variables, and so we have this assumption which essentially says that the inverse of the transformation sigma theta is unique and is continuous. C.R. Rao has called this the condition of strong identifiability, and it really amounts to global condition of global identification. Now, I define the small l of theta and s. Here is the logarithm of the covariance matrix and the trace of the sample times the inverse of the population covariance matrix. So this is the likelihood function of the Wishart density. We take the negative of it and standardize by multiplying by 2 over n. This is essentially the likelihood function of the observation, based on the observations themselves, except for the matter of using the little n degrees of freedom or the capital N number of observations. Now, it's convenient to define, this is the likelihood function, dropping out things like powers of 2 pi and so on, that are irrelevant to the maximum likelihood method. We can further modify that quantity by subtracting the log of the determinant and the dimensionality p, so that we have a function of 2 matrices, which is a kind of discrepancy function. It's termed by Brown. It has the property that if the 2 matrices are different, this quantity is positive, and if the 2 matrices are the same, this quantity is 0. Now, I've talked about maximum likelihood under the assumption of normality, but equivalently I can say that I'm simply going to define an estimate which minimizes this discrepancy function. And when put that way, it sounds like normality isn't so important. Now, for some technical reasons, we make some more assumptions. I use the notation that if we take a matrix and string its columns into one long vector, then that operation is denoted as the vec of that matrix. So our assumptions are that this function, the loading matrices are functions that are differentiable, so there's a regularity condition. And the second condition here is that this matrix of partial derivatives is of maximum rank, which is really a condition of local identifiability. But then we define the maximum likelihood estimate as the parameter value that minimizes that function, or equivalently that minimizes the discrepancy function. And the first result is that if the covariance matrix is consistent, then this maximum likelihood estimate is consistent. And that follows readily from our definitions and properties. Here, the estimate theta caret minimizes this discrepancy function, so it's less than or equal to the discrepancy between the population value. I use the subscript 0 to indicate a parameter value of the population sampled, often called the true value. Now, the discrepancy function of the true value in the sample covariance matrix converges, well, S converges to sigma of theta naught by assumption, and as we saw, then this discrepancy function is 0, so the discrepancy using the estimated covariance is trapped between 0 and this quantity that's approaching 0, so it approaches 0, but that implies that the two matrices are the same asymptotically, and S is going to the population value, so that implies that the covariance matrix of the estimate goes to the covariance matrix of the true value, and by the global identification condition, that implies the final probability limit. Well, now what about the asymptotic normal distribution of the estimates? We can go the usual route of taking derivatives and setting them equal to 0. We're not going to go through all the details, but just outline the development. So we have, again, this function that's equivalent to minus 2 over n times the log of the likelihood function, and we take the first derivative with respect to theta. Now, in taking derivatives with respect to theta, I mean we take derivatives with respect to the components and then string them out in a column vector. So this first term comes from the log of the determinant. The second term comes from the trace term. If we rewrite it as indicated here, remember we're putting derivatives into a long column, then we can finally write it in a more convenient notation using this vec operator that pulls out the S minus sigma of theta. The two sigma inverses go into a Kronecker product, and the partial derivatives are put into another vector. Now, the important thing of this is that these derivatives are a linear function of the difference between the sample covariance matrix and the covariance matrix of the parameter as a function of the parameter. Now, the usual procedure of getting asymptotic theory for maximum likelihood estimates is to expand the derivative function, the derivative of the log likelihood, And I've written that down here. This is familiar procedure. So by using our familiar Taylor's theorem, the first derivative at the maximum likelihood estimate is the first derivative at the population value plus the second derivative at some intermediate value, that is on the line segment from the estimate to the true value, times that increment in theta. And then by virtue of the regularity conditions, the second derivative, so-called Hessian or multiple of the Hessian, converges in probability to a positive definite matrix. And when we solve here for theta caret minus theta naught and replace sample values at consistent estimates by population values, we get this expression down here. Again, the important thing to note is that the difference in the estimates is a linear combination of the difference between the sample matrix and the population matrix. So that means that if we have a central limit theorem operating on the sample covariance matrix, then we get asymptotic normality of the maximum likelihood estimates, or minimum discrepancy estimates. So I've written that down here, that if the sample covariance matrix has a limiting normal distribution, then the estimates have a limiting normal distribution. And if original assumption that the observations were normally distributed, then by the usual maximum likelihood estimate, we know what the covariance matrix is. Now, you usually get the information matrix, the inverse of that. There's a factor of 2 here because of the way we define this little L of theta and S. Well, so far I haven't used the linear structure that I had written down first. So now I want to use that linear structure. So you remember we had these latent variables, the z's, and the x's were linear functions of the z's, so the covariances of the x's are going to be quadratic functions of the z's. So we define here the sample covariances of the latent variables, covariance matrices of the latent variables. These, of course, are unobservable, but they're behind everything that we do. And now I define a vector which is partly a population vector, that is, lambda 0 is the population value, the true value of that vector of parameters, but the rest of this are sample quantities. They're made up of variances and covariances of the latent variables. So the difference, instead of having theta caret minus theta naught, we have theta caret minus theta n, and you see up here that involves a subvector of theta caret minus theta naught, but then some sample quantities. This should have a caret on top. Now, there's nothing that says that we have to expand the likelihood function around the true value. We can expand the likelihood function around this hybrid vector, this theta n. So I've written down here the same algebra that we had on a previous transparency, but the expansion is in terms of the maximum likelihood estimate minus this hybrid vector. And that's the second derivative is evaluated at some value on the line segment from the estimate to this theta of n. Again, the theta double star is a consistent estimate of theta because theta n is a consistent, converges to theta naught. So we get the same kind of solution for the difference between the estimate and this hybrid vector, but this is now a linear function of the sample covariance matrix minus the covariance matrix that's calculated from the hybrid vector. And this is what leads us to general results. So let's just take a look at that difference, which is on this transparency. We have the sample covariance matrix. The x's are linear functions of the latent z's. So I've written it down here once with a subscript g and the transpose with the subscript h. And when we interchange the summation on observation index and subvector index, we get the covariance matrix is a linear function. The observable covariance matrix is a linear function of the unobserved covariances. Now, we saw earlier that the covariance matrix as a function of theta is written this way. That is, this population quantity, this function, is like what we had before, but there are no terms with an index g and h because the z's in the population are uncorrelated. So if I now replace this theta by theta n, we get a linear combination now of the covariance matrices of the g's. The point of the difference here is that we get all the combinations of g and h up here, but here we only get the terms where the g and h are equal. So we take the difference, the terms involve g and h being different. And that is the key to this development. So we now want to weaken the assumptions so that instead of assuming, well, they're weakened and they're strengthened. We now assume that these individual subvectors are independent. Before, we've been assuming that they're uncorrelated. So this is a strengthening of the assumption. But otherwise, we just ask that they're independently, identically distributed, which, and that their second-order moments exist. If that is the case, then these sample covariance matrices with different indices have a limiting normal distribution. And the argument is carried out here. The main point is that terms like variances of products, because of the independence, are products of variances. As this is a typical product where the index I refers to subvector G and an index J refers to a different subvector with index H. The outcome is that the covariance, the unobservable covariances with different indices have a limiting normal distribution, and those covariances of the limiting normal distribution only depend on second-order moments. So the final result, then, is that the difference between the sample covariances and this sigma evaluated theta of n has a limiting normal distribution under assumption 3, and therefore by the previous development, this difference vector has a limiting normal distribution. And among other things, this limiting, this vector is the difference between the lambda and that is the estimate and the true value. Now, the point to this is that the limiting normal distribution doesn't depend on the distribution of the latent variables. whether they're normal or something else, as long as they have second-order moments. Now, the assumptions can be weakened further. We can ask that, we can suppose that one of the subvectors is almost anything as long as its second-order moments are consistent estimates of something. So they can be random or non-random or combinations of that. In that case, the second-order sample moments have a limiting normal distribution, and this estimate will have a limiting normal distribution, which again depends only on the lambda naught, the population value, and these population second-order moment matrices. So while the estimates depend on the matrix S, which is second order in the observations, the normal distribution of S would depend on fourth order moments of the X's, but what we're interested in only depends on second order moments. Let me just close by showing that, just reminding you that this does apply to the factor analysis model and to the linear structural relations by translating the model back to those special cases.